Hi guys, it's Mrs. Nicolosi. Today we're going to be starting a unit on gases, and in this lesson I'm going to be discussing gas behavior, Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. So we're going to start off by talking about something called the kinetic molecular theory, which explains the behavior of gases. The kinetic molecular theory can lend itself to any type of matter, solids, liquids, gases, but today we're going to be focusing on gases. The idea of the kinetic molecular theory is that it is based on the fact that particles or molecules are in constant motion. Kinetic is the energy of motion. So the kinetic molecular theory of gases is based on these 5 assumptions here. And they basically explain how gases are going to behave in an ideal or perfect world. The first assumption is that gases consist of large numbers of tiny particles that are far apart relative to their size. The distance between the particles is what separates gases from liquids and solids. Liquids and solids, their particles are much closer together, whereas once they become gases, those particles spread much farther apart. The second assumption is that collisions between gas particles are considered to be elastic collisions, which means that they are not losing any kinetic energy. So the idea that these particles can bump into each other or bump into the container that they're in and not lose energy is what we call an elastic collision. It's a collision where no energy is lost, and those particles will bounce back with the same amount of energy that they hit something with, whether it's another gas particle or a container. The third assumption is that gas particles are in constant, rapid, random motion, and that they possess kinetic energy, which we said is the energy of motion. Now, the important thing here is to remember this constant, rapid, random motion of gases. We do not have the ability to predict their motion, and that's what sets gases apart from other types of matter. Number 4, there are no forces of attraction or repulsion between gas particles. And this goes along with the idea of elastic collisions. Because gas particles are not being attracted to or repelled from one another, they are considered to not have any force of attraction or repulsion, and that is where the term elastic comes from. And finally, number 5, the average kinetic energy of gas particles depends on the temperature. So if you heat up a sample of a gas, the particles are going to move around a lot faster than if you cool it down, and then in that case, they'll move a lot slower. Now, no gas behaves as what we refer to as an ideal gas, but most gases behave very close to this. And so that's why we use this ideal set of conditions in our discussions on gases. The things that allow gases to deviate from ideal behavior is if the temperature is too low or the pressure is too high, and then they start to do weird things and act like liquids, but they're really not. And we won't get into any of that. We're going to be primarily focusing on ideal gases. Gases have the ability to expand to fill their containers completely. This is something that liquids and solids do not have. Liquids can fill their container, but not necessarily completely. They'll just take the shape. And solids will not take the shape of their container whatsoever. Solids and liquids both have a fixed volume, whereas gases will expand to fill whatever volume that they are given. Fluidity is another property of gases, and this is the ability for particles to slide past one another. When we think of fluids, we often think of liquids, but gases are considered to be fluids as well. Low density is also a property that is unique to gases, and in comparison to that of liquids or solids, gases have the lowest density of them all. Gases also have the ability to be compressed, so we can smush the particles together and they can take up less space, or we can let them expand to fill their containers. That's something that we can't do with liquids and solids. Diffusion is something that is not unique to gases, but it happens a lot faster with gases. So your liquids and your solids will slowly diffuse, but gas particles will diffuse much faster. And that's why you smell things in the air. For example, like if you're driving down the road and you smell a skunk, that's because the diffusion of those gas particles has happened very quickly, and you probably smell it long before you'll see it. And finally, effusion is the ability for gases to escape out of a tiny hole or opening. Now, that doesn't sound like rocket science, but what is important there is that the smaller the particle, the faster it's going to escape out of that hole. The bigger the particle, the longer it's going to take. So we're going to be focusing on some specific units of measurement in this unit, and the first is pressure. We're going to be measuring pressure of gases, and pressure is a very important property of gases, and it allows us to understand their behaviors. So pressure can be given in a number of different ways, and it's important for us to be able to relate those different ways to one another in order to convert one unit from another. So here we have a table of the different units of measurement that you'll see when we are talking about pressure. Pressure can be measured in millimeters of mercury, which is probably the most common unit used in measuring atmospheric pressure. Atmospheres, that'll be used a lot in scientific measurement. Pascals and kilopascals. Torr, which is not as common, but it's the same thing as a millimeter of mercury. And as you can see over here, our conversion factor at normal atmospheric pressure, they are the same. And then finally, pounds per square inch, which is exclusively used here in the United States, where we use that English measurement system with inches. Temperature is another factor that we're going to take into account when we're talking about gases. And if you can recall, there are 3 ways that we can measure pressure: Kelvin, Celsius, or Fahrenheit. We're going to be focusing on the Kelvin and the Celsius scale in this unit. And you'll never be given a Fahrenheit temperature asked to convert something into Fahrenheit. We will be ignoring the Fahrenheit scale for this one. And Kelvin and Celsius are really easy to convert. The unit of the degree in each scale is the same magnitude. It's just where this scale starts that's different. So the Kelvin scale is based on absolute 0, so it starts at 0. Whereas 0 in the Celsius scale is the freezing point of water, so that's a little bit higher than the freezing point of everything. But it's important to know how to convert between Celsius and Kelvin, and the way to do that is to add or subtract 273. Kelvin is equal to the Celsius temperature plus 273. Now, there's a special set of conditions that we refer to as standard temperature and pressure, or STP. And these conditions are ones that are often present in reaction settings in the lab and things like that. And they're a very common set of conditions. So they have their own unique name. And when we say STP in a problem or in an experiment, you want to automatically think STP means 1 atmosphere and 0 degrees Celsius. Now, at this particular set of conditions, we know that 1 mole of any gas is equal to 22.4 liters of volume. So we can use that as a conversion factor to go between moles and volume of gases, but that's specific to gases. And we'll get there when we start talking about gas stoichiometry. Now, what we're going to be focusing on today as far as calculations are something called the gas laws, and we're going to be talking about 4 of them today. There are several more. We're going to limit our discussion today to the first 4, and then we'll pick up with the ideal gas law a little bit later. Boyle's law is the first of the gas laws, and it's the relationship between pressure and volume. Pressure and volume are what we refer to as inversely proportional, as long as the temperature is being held constant. And what an inverse proportion is when one goes up, the other goes down, and vice versa. So you can see here in this image, when the pressure is 1, the volume is 1. But if we increase the pressure, if we double the pressure to 2, then the volume gets cut in half to 0.5. And so we use that relationship, and we can put it into a formula. P1V1 equals P2V2. P1 and V1 would be the first set of pressure and volume conditions. P2 and V2 would be the second. You'll always be given 3 and then asked to find the one that's missing. So here's an example using Boyle's law. A sample of oxygen gas has a volume of 150 milliliters when the pressure is 0.947 atmospheres. So notice our units for volume are milliliters. Our units for pressure are atmospheres. It's important for you to be able to recognize the units as we go through these problems. What will the volume of the gas be at a pressure of 0.987 atmospheres if the temperature remains constant? That little key at the end there tells us that we can use Boyle's law and the relationship between pressure and volume. So I start by listing what I know, and then I look at my relationship to see what's missing. I am solving for V2 here. So I'm going to plug in everything I know and solve for the missing volume, which is 144 milliliters. And that makes sense because as I increase the pressure, the volume should decrease due to that inverse relationship. Next, we have Charles's law, which is the relationship between volume and Kelvin temperature. It's very important that the temperature is in Kelvin. Volume and temperature are directly proportional, which is the opposite of what we just saw with Boyle's law, which means that as volume increases, temperature increases as well. If volume decreases, temperature is going to decrease. So instead of multiplying the first two conditions, we are dividing. So V1 over T1 equals V2 over T2. And here's an example using Charles' law. A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 degrees Celsius if the pressure remains constant? So I know my volume 1. I list my temperatures in Celsius, but remember, this is all based on Kelvin temperatures, so we have to add 273 to get our Kelvin temperatures, and then we're solving for V2. So when we set up our calculation, volume 2 would be 815 milliliters. Now, the third gas law that we're going to discuss today is Gay-Lussac's law, which is the relationship between pressure and temperature. Pressure and temperature are directly proportional, just like the volume and temperature that we saw in Charles's law. So P1 over T1 equals P2 over T2. We'll apply that to an example as well. The gas in an aerosol can is at a pressure of 3 atmospheres at 25 degrees Celsius. Directions say that it cannot exceed the temperature of 52 degrees Celsius. What would the gas pressure be at 52 degrees Celsius? So again, I list what I know, convert my temperatures, and solve for what's missing. And that missing pressure would be 3.27 atmospheres. And finally, the combined gas law, which is a combination of all three of the laws, combining pressure, volume, and temperature. So nothing is held constant except for the volume of our gas, except for the fixed amount of our gas, rather. We have a set amount of gas, and we're looking at how the pressure, volume, and temperature will all fluctuate. So a helium-filled balloon has a volume of 50 liters at 25 degrees Celsius and 1.08 atmospheres. What volume will it have at 0.855 atmospheres and 10 degrees Celsius? Again, I'm listing everything I know. In this case, I'm solving for the second volume. It's asking what volume will it have. And so I plug all my numbers in and solve for the missing volume, which in this case is going to be 60 liters. All right, so I'm going to stop there for now. We'll go through a couple more examples from the worksheets that you're going to be assigned dealing with the gas laws. And we will pick up with notes on the ideal gas law in a few minutes.